A curious chemistry student analyzed the 10 milliliters of solution D to determine the concentration of iron 2 plus ions by titrating acidified solution to the standard solution of potassium permanganate. A 10 milliliters of solution was titrated with potassium permanganate solution of concentration 0.02 molar. Volume of potassium permanganate used for this complete reaction was 37.5 milliliters. Now, first question be given, calculate the oxidation state of manganese in potassium permanganate. So potassium permanganate gave us these ions which you are seeing here. And so we have been given Mn4 minus. Now, what is the oxidation number of manganese? Now, if we can look at this, manganese is just one atom, and then plus we have got 4 atoms of oxygen. Now each oxygen, the oxidation number is -2, and this should give us the sum of the oxidation numbers of manganese and 4 atoms of oxygen should be equal to the charge, which is -1, and so this gives us manganese. Okay, so that will be a minus. Now manganese minus 8 is going to be -1, and so the oxidation number for manganese will be 8 goes the other side, -1. That gives us the charge for manganese is in this case +7. We need to include the positive. Alright. Now the next question given is this B is part A. Part B says find the number of moles of permanganate ions used. Now the number of permanganate ions used, look at the information given. We've been told 0.02 mole per liter, that is the concentration of potassium permanganate used for complete reaction. Okay, so these are the moles. Starting from this point here, 10 milliliters of the solution was titrated against potassium permanganate of concentration 0.02 mole per liter. Volume of potassium permanganate used for complete reaction was 37.5. And so to find the number of moles, as B is asking, number of moles of this potassium permanganate. Potassium permanganate is like that. Now the potassium, we can't see it in a redox reaction because it was a spectator ion, it disappeared, and so finding the number of moles potassium permanganate is just the same as finding the number of moles of what? The manganate ion, and that is equal to concentration times volume. Now the concentration in this case is 0.02 mole per liter. We've been given mole per liter, and then multiply by the volume. So the volume which was required was at 7.5, and so converting that, because it is in milliliters, converted to liters by multiplying by 10 to the power -3. And so the number of moles that we are going to find is 0.00075 moles of manganate ion. Alright, and then C asks us to calculate the number of moles of ions. Okay, iron 2 ions. So the number of moles of iron 2 ions, they are there. Now to calculate the number of moles of that one, just going to use the mole ratio. We can see that the number of moles of iron 2 plus, the number in front there is 5, should be equal to the number of moles of the manganate over what? Over 1. That's the number in front, as we can see. And so this is going to give us number of moles of iron 2 plus being equal to, just multiply 5 by that, so it will be 5 times the number of moles of the manganate. So that will give us 5 times the number of moles of the other one already calculated, 0.00075 moles. And so if we cross multiply, that will give us 0.00375 moles of iron 2 plus. Right. Another question given, pure sodium sulfite is difficult to get. One method of assessing its purity is by the reaction of potassium manganate 6 in acidic solution according to the unbalanced reaction we can see there. The sodium sulfite is slowly oxidized in air to sodium sulfate. 1.75 grams of an impure sample of sodium sulfite was dissolved in water, and made up to 250 cubic centimeters with distilled water. And then 25 cubic centimeters of this solution required 22.8 cubic centimeters of 0.0216 molar potassium manganate to complete oxidation. We've been given the molar mass. Now, the first question we've been given starts from here. Balance the equation in acidic media. So that is the first one. Now, how do we balance this equation in acidic media? So the first thing that we are going to do is want to break it into two half reactions. And so this is related to this portion. And then this is related to that portion also. And so to balance that, we are going to write Magnesium O4 minus, that going into what? Magnesium 2 plus. And then we have got a sulfate SO3 2 minus, and that is going into what? SO4 2 minus. So these are just going to come in themselves as you balance the hydrogen ions and water. And so now what we can see here, to balance at this stage, to balance, now you can see that we have got oxygen on one side, 4 oxygens, but on the other side we don't have any oxygen. And so to the side that has got no oxygen, we're going to add 4 water molecules. Okay. Now notice that for the first reaction, immediately you add 4 water molecules, you've introduced 8 hydrogen ions. And so to the other portion, we are going to add 8 hydrogen ions. Now for the second reaction, we have got 3 oxygens, we have got 4 oxygens. So this portion is one less oxygen than the other portion. And so we are going to have 1 water molecule the other side. Whenever you want to balance oxygen, you add water. Now when you introduce 1 water molecule, you've introduced 2 hydrogens, and so the other side we are going to add 2 hydrogen ions in that manner. Okay, now look at this. For this first half reaction, what are the charges we have? We have got 8 positive charges, and then all this compound we are saying here is negatively charged. So we have got 8 positive charges, and then we have got 1 negative charge on the reactants. And then on the products, we have got this thing is as a positive 2 charge. Water is not a charged molecule, the charge is 0. As you can see, we don't have anything on top there. And so this is going to give us positive 8 minus 1 is going to be positive 7. And then positive 2 plus 0 would simply be positive 2. If we go to the other half reaction, this is not charged. And then this thing has got a negative 2 charge. And so I've got a negative 2 charge on the reactants. Going on the products, this one has got a negative 2 charge. This one, positive 1 charge, but because there are the 2 of them, so that is going to give us positive 2 charge. So it is moving from negative 2 to positive. Negative 2 plus 2 is a 0. Now to the side which is bigger, we are going to remove a certain number. So what we are saying is, what number can we remove from positive 7 for us to reach to positive 2? It's really 5. So now to the side where we want to remove, removing is the same as adding electrons. So we are going to add 5 electrons on the reactants for the first reaction. For the second reaction, this is bigger. 0 is bigger than negative 2. Now what number can you remove from 0 to get to 2? Is 2. So 0 minus 2 is going to give us negative 2. And so removing 2 is the same as adding 2 electrons. So that becomes it. And so this is telling us that for the first half reaction, on the reactants we are going to add 5 electrons. And so that will be 5 electrons plus 8 hydrogen ions plus that producing this compound. For the second half reaction, on the products we're adding 2 electrons, so that will give us water plus a sulfite ion to produce a sulfate ion and 2 hydrogen ions and also 2 electrons. Now at this point we need to balance out our electrons. We have got 5 electrons here, we've got 2 electrons here, so we're going to swap those numbers. So this reaction we're going to multiply it by 10, by 2. We're going to get these 2. And then the other reaction we're going to multiply it by 5, coming from the 5 electrons which are there. And so that will give us 2 times 5, which is 10 electrons, 8 times 2, which is 16 hydrogen ions, and then plus 2 manganate ions, and then we have got 2 manganese 2 plus, and then we've got 8 water molecules, and then 5 times the other one, that would be 5 water molecules plus 5 sulfate, and then that is going to produce also 5 sulfate, that was a sulfite, and that would be 5 times 2 hydrogen ions would be 10 hydrogen ions, and then plus 10 electrons. Now reaching at this point, we're going to cancel out what is the sum. So we're going to divide this reaction into 2 portions. So we're going to cut it at this point. Everything we can see on this side, these are reactants. Everything this side, those are products. So what is appearing on the reactants and products, we're going to cancel out. Electrons are appearing there, 10 electrons are appearing there. 5 water molecules there, 8 water molecules, so only 3 water molecules are going to remain. And then we have got 10 hydrogen ions, 6 hydrogen ions are going to remain here. So now we're going to join what is on the reactants on both the reactions. So here we've got 6 hydrogen ions, and then plus we have got this compound, which is 2 Mn4 minus, and then we also have this, which is 5 sulfate, like that, and that is going to produce, now we go on the products, we have got this, which is 2 Mn2 plus, and then we have got this, which is 5 sulfate 2 minus, and then we have got now 3 water molecules. So this becomes now the balanced redox reaction. Now part B, we've been asked, calculate the change in oxidation number of sulfur in the reaction. So 1 in is not supposed to be there. In the reaction of sulfite with manganate. So when this sulfite reacts with this manganate, what is the oxidation state? Okay. So we want to calculate the oxidation, the change. Now we're talking of change. So sulfur is changing from this one, and then it's going to go to this one. So we're going to calculate the oxidation state of sulfur on the reactants. So on the reactants we have got, since this is 5, this is also 5. Let's leave those out. Let's just get a sulfite. So on the reactants we've got a sulfite ion, and then on the product we have got a sulfate ion. We want to calculate the change in oxidation number. So here we have got sulfur plus we have got only 3 oxygens, and we know that this oxygen is -2 charge, and this should give us the total charge, which is -2. If we go on the products, we want to find the oxidation state of sulfur, and then we have got 4 oxygens, and each oxygen we know is -2 charged, and then this should give us a charge which is also -2. This is going to give us sulfur -6 being equal to -2, producing sulfur -8 being equal to -2. So if we take 6, the other side becomes positive. 6 minus 2, that will give us +4, and that is going to produce on the product. If we take sulfur, the other, -8, the other side becomes positive. It will be 8 minus 2, which will be +6. Now change in oxidation number for the sulfur. Change is what is on the product is +6, and then minus what is on the reactants is +4. That is going to give us what? +2. So that is the change in oxidation number. Okay. Now if we go to the other question, so apart from that, the other question is calculate the number of moles of manganate 6 ions used in this titration. So from here, calculate the number of moles of manganate ions used in this titration. Now we've already been told, the information has been given here. So number of moles of manganate ions is going to be equal to concentration times volume. Now we've been told that we got 25 milliliters of solution and then reacted with 22 0.8 milliliter of what? 0.021 molar potassium manganate. It is from this potassium manganate that we got the manganate ions, and so the concentration has been given as 0.0216 molar, which is mole per liter, and then multiply. Now the volume is given as 22.8 in milliliters. Convert that to liters by multiplying by 10 to the power negative 3, and so that is going to give us 0.00049248 moles. Okay, now the other question is calculate the number of moles of sodium sulfite in 25 milliliters of solution. Now get this, sodium sulfite from this point which is here, sodium sulfite slowly oxidized to air. 1.75 grams of impure sample of sulfate was dissolved. Okay, so this was actually supposed to be sodium sulfate. The impure 1.75 grams sample of sodium, impure sodium sulfate, was dissolved in water and made up to 2. So when we dissolved this mass in water, it is impure, remember. After dissolving in water, we added, okay, we added more water to make sure that the volume reached to 250 milliliters. Now, we didn't get all of it, we only got 25 milliliters. That's the one that we mixed with potassium manganate. And so, to find the number of moles, as the question is asking, calculate the number of moles of sodium sulfite in 25. So that is actually the number of moles of sodium sulfite which reacted. And so, from the sodium sulfite, that is where we got a sulfate ion. So using the balance reaction, I'm going to say number of moles of this manganate, or for minus. Now the coefficient, the number in front of the manganate is 2, should be equal to the number of moles of the sulfite ions over what? The number in front there is 5. So the number of moles of the manganate we've already found as 0.00049 and then divided by 2. This should be equal to the number of moles of sulfite over 5. And so multiply this by that. And so we're going to remain with number of moles of sulfite to be equal to, if we multiply, we divide this value on top by 2 and then multiply it by 5, what we are going to have is 0.0012312 moles of a sulfite ion. Now the other question says, calculate the total, okay, before that, calculate the total number of moles of sodium sulfate in 25 milliliters of solution. Calculate the total number of moles of, calculate the total mass of pure sodium sulfate in 250 milliliters of solution. Okay, so this is actually a very interesting question. So let's go on. Now, as I said earlier, this first was dissolved to make this volume. Now this volume only got this portion. Okay, now to determine the number of moles of sulfite in what? In 250 milliliters. What we'll do is we are going to just get the number of moles which you've already calculated. These are the moles, remember, in 25 milliliters. So the moles in 25 milliliters, okay, we are going to multiply them. Now these are in milliliters, so we're going to say, since we have calculated the number of moles in 25 milliliters, how many 25 milliliters are in 250 milliliters? Because we want to find how many moles are in there. And so we'll multiply by 250 milliliters over 25 milliliters, and that is going to give us a value of 0.0012312. Okay, there's only 1 0. It's the same value that is just 0.0122312 moles of a sulfite. Now, after finding this, we want to calculate now the total mass, because we needed first to calculate the moles in 25 milliliters before we found the mass in 25 milliliters. And how do we find the mass if we know the number of moles? So mass is actually given by number of moles times molar mass. Now the question is calculate total mass of pure sodium. This is sodium sulfate. I think they already gave us the molar mass of sodium sulfate at that point. And so the number of moles is 0.012312, and then times now the molar mass. The molar mass in this case is where the molar mass is already there, which is 126.05. So let's just punch on the calculator, we see the value find 0.012312 multiplied by 126.05. So that is going to give us 1.55 grams of sodium sodium sulfite, because the number of moles of a sulfate are equal to the number of moles of sodium sulfate. Okay, that is what we all need to get. The number of moles of the sulfite ions which you find are equal to the number of moles of sodium sulfite that are going to be there. Now the next question is calculate the percentage purity of this sample of sodium sulfite. So percent purity is actually equal to mass of pure substance, mass of pure sodium sulfite, over the mass of sample, the whole sample, which is impure. And then we multiply that by 100%. Now the pure one which we've just calculated is 1.55. And then the sample we are given, the mass is there, is 1.75. All these are in grams. And now multiply by 100%. And so, let me write it here. The mass, the percentage is 88.68% purity. So that is the percent purity for this substance then. Given another question here. In an experiment, a sample of 0.7 gram of hydrated iron sulfate solution was acidified with sulfuric acid and titrated with a standardized potassium permanganate solution according to the balanced equation shown there. And then it required exactly a mean titer volume of 25.05 milliliters of 0.02010 molar potassium permanganate solution to reach the end point. Now the first question, calculate the moles of iron 2 plus in the hydrated iron sulfate. Okay, so the number of moles of iron 2 plus in that solution should be equal to the concentration times the volume. Now we've already been told what information has been given here. Okay, we are told that for the 0.7 gram hydrated iron sulfate solution, that thing required exactly a mean titer volume of 25.05 of 0.0210 molar potassium permanganate. So we know we first know the volume of potassium permanganate and also the concentration of potassium permanganate. Now, having known this, we can determine now the number of moles of what? A manganate ions, before we can even find the number of moles of these other ones. So from what we can see from here, from the formula, since this is a balanced equation, number of moles of iron 2 plus over 5 should actually be equal to the number of moles of the manganate ions over what? Over 1. And so if we cross multiply, that will give us number of moles of ion 2 plus just being equal to 5 times the number of moles of the manganate ions, like that. But how do you find the number of moles of the manganate ions? That is concentration times volume of the manganate ions. Okay, so we're going to say 5. Now the concentration we've been told that is 0. So at this point, the concentration has been given as 0.02010 mole per liter. And then multiply that by the volume, which is 25.05. Now multiply that by 10 to the power negative 3 to convert it to liters, because it's given in milliliters. And so let's go on and punch on the calculator. So that will be equal to 5 multiplied by 0.02010, and then also multiplied by 25.05, and then multiplied by 10 to the power negative 3. So the number of moles that we are supposed to find is 0.002517525 moles of what? Ion 2 plus. To give our final answer, notice that what we used, this was in 4 significant figures, this is also in 4 significant figures, so give it in 4 significant figures. That will be 0.002575 moles to 4 significant figures of ion 2 plus. Now the other question we've been told, these are the moles of ion 2 plus in hydrated iron sulfate. Calculate the molar mass of iron sulfate. Now how do we determine the molar mass? Okay, so these moles that you found for iron 2 plus is actually equal to the number of moles of hydrated iron 2 sulfate. That is what we need to get to understand. The moles we've calculated is equal to the moles of these. Okay, that is because in one, if we have got one of this compound, we only have one ion there, and so the number of moles are the same. So to find the molar mass, we know that number of moles is given by mass over molar mass, and so molar mass is going to be equal to mass, in this case, okay, that will be mass times, it will be like that, and then we are going to have mass this side. So molar mass will be mass over number of moles. So we have got the mass and then the number of moles there. So the molar mass therefore is going to be, now, sorry, this is number of moles, not molar mass again. Okay, the mass which we have in this case, we've been told 0.700 gram of hydrated iron 2 sulfate is what reacted. So that was 0.700 grams, and then divided by the number of moles, which is 0.00257525. You'd rather use the one which you found here before rounding off to be to make sure just that we are precise and much accurate. So 0.700 divided by that answer. So the mass that I'm finding is 278.0508634 grams. Because this is molar mass, it is in grams per mole. Okay, to give the final answer, I can say 278.1 grams per mole. Alright, now the other part we've been going to determine the water of crystallization. Determine the water of crystallization. So the water of crystallization that we are talking about here is this X that is here. Okay, now how do we go about that? So we're going to get this ion. If we find the molar mass of this compound, the molar mass of this ion, hydrated iron 2 sulfate, like that, is supposed to give us the same number of moles I mean the same molar mass that we've already calculated there is 278.050 0.278.0508634. So that is supposed to be the molar mass that we need to find. But how do we find the molar mass if you've been given a formula? We only have one ion here, and so that is going to give us this one ion. We go on the periodic table, we get the molar mass of ion. So from the periodic table, the molar mass of ion is 55.845. And then we've got one sulfur. The molar mass on the periodic table for sulfur is also giving us 32.065. And then we've got 4 oxygens there. Then the molar mass for each oxygen, 15.9994. And then plus. Now these two, we are going to find them together and then multiplied by x. So the molar mass of water, H2O, oxygen is 15.9994, and then we have got 2 hydrogens each with 1.008 molar mass, and so the molar mass we are going to find supposed to be 18.02. So this 18.02, there is an x in front there, so we're going to multiply it by x. 18.02 multiplied by x, and so all of this is supposed to give us the molar mass which we've already calculated as 278.0508634. So if we work out this on the calculator and punch them, we are going to find 131.92 plus 18.02x, and that should give us 278.0508634. So taking this value the other side, we're going to remain with 18.02x being equal to 126. So that will be 278.05 minus 131.92. That will give us 126.1308634. Now divide by 18.02 on both sides. So x then is going to give us 6.999422977, and so this x approximates 7. So that is the order of crystallization then, is 7. Another question given here. Solution of iron 2 ions can be analyzed by titration with potassium manganate. The balanced equation is shown there. A student made 250 cubic centimeters of solution of iron 2 sulfate of concentration 0.103 molar. Having run out of time and unable to continue his experiment, the solution was left overnight in the beaker, and then titration of it was left overnight in the beaker. Titration of 25 cubic centimeters portion of this iron 2 plus iron 2 sulfate solution with 0.02 molar potassium manganate solution the next day required on average 23.7 cubic centimeters of solution for complete oxidation. Now, first question we've been given. So A here, calculate the number of moles of potassium manganate. The first question. Now, how do you calculate the number of moles of potassium manganate? So the number of moles of potassium manganate, remember from the potassium manganate, that's where we are getting the manganate ions. Now the potassium is a spectator ion, that's why you can't see it here. It cancelled out as we are deducing an ionic equation. So if you find the number of moles of manganate, you've already found the number of moles of potassium manganate, and that is going to be given by concentration times volume. Now we've been taught from the statement, which is a titration of 25 cubic centimeters of this portion with 0.02 molar potassium manganate the next day required on average this volume. So this is the volume of potassium manganate of this concentration, which we did react with 25 cubic centimeters of what we've been given. And so to find the number of moles, multiply the concentration, which is now 0.02 molar, which is mole per liter, then multiply by the volume which we used, which is what, 23.7. Now this is in cubic centimeters. To convert these cubic centimeters to cubic meters or to liters, we need to get to know that 1 liter is equal to 1 cubic decimeter. So we want to convert these cubic centimeters to cubic decimeters. So that is what we want to do. Now that is just simple by multiplying by 10 to the power negative 3. So we've already converted cubic centimeters to cubic decimeters, because if we are talking of molar, molar is the same as mole per liter or also mole per cubic decimeter. So these two are the same. So if we convert to the other, that means we've already converted to the other also. So we're going to say, instead of decimeter cubed, let me put liter, so that we are going to cancel out like that. And so that is going to give us 0.000474 moles. So these are the moles of the potassium manganate. As I said, I've just put a K there, because that's the one they asked for. It's equal to the number of moles of the manganate ions themselves. Now for the second part, B, so that was our A. For B, we want to calculate the number of moles of ion 2 present in 25 cubic centimeters of solution. Okay. How do you calculate the number of ion 2 ions? Now look at the balanced reaction there. So number of moles of ion 2 plus divided by 5 should be equal to the number of moles of the manganate divided by 1. And this is going to give us number of moles of ion 2 plus being equal to just 5 multiplied by the number of moles of the manganate. And so this is going to give us number of moles of ion 2 plus being equal to 5 times the number of moles of the manganate, which we already found is 0.000, that is 474 moles. So this will give us 0.00237 moles of ion 2 plus. Okay, so those are the moles. Okay, now we've been given part C, hence calculate the number of moles of ion 2 plus present in 250 cubic centimeters of solution. Remember, a student first had a solution of this volume, okay, with this concentration which is here. Now having run out of time, the student couldn't continue with the experiment, and so the solution was left overnight. Now the following day, only titrated what? 25 cubic centimeters of this ion 2 sulfate, the same one which is there, just titrated only 25 cubic centimeters of that portion. Okay, in other words, he just used the portion, he didn't use everything. And so to find the number of moles of ion 2 plus in now the 250 cubic centimeters, simply multiply the same number of moles which reacted, the 0.00237 moles. Now multiply how many. So this is the number of moles in what? In 50. I mean in 25. That's what reacted. So now how many of 25s are present in the whole of this solution? So we'll say 250 cubic centimeters divided by 25 cubic centimeters. The cubic centimeters are going to cancel out, and so that would simply be a ratio. And that is going to give us, when we do the multiplication, 0.0237 moles of ion 2 plus. Okay, now the other question asked, what percentage of the ion was oxidized? Now, remember, initially we are given this concentration of ion. Did everything get oxidized? So to tell if they did or not, first let's convert these moles that we have into concentration so that we can compare with the concentration that we are given. So the number of, so now what we want to find is the concentration, the molarity. The molarity of iron 2 plus in 250. This is what got oxidized because after the reaction occurred, only this was used. That means it's the one which was getting converted to what? To the iron 3 plus. So that is the one which got oxidized. Remember, oxidation is increase in oxidation number. Okay. So, and how do we find molarity? Simple number of moles over volume. Now the number of moles is 0.0237 moles. The volume, remember this happened in which volume? In that volume of 250. Now we need to convert that to liters or to cubic decimeters, or the same. And so that is going to give us, if we convert, 0.0948 molar. So these are the ones which got oxidized, but we were given initially these moles. Now what percentage got oxidized? Well, to find the percentage, we just compare what got oxidized and then what was given. So percentage of iron 2 plus which got oxidized will be equal to the molarity of what got oxidized, which is 0.0948 molar, divided by the whole molarity of everything that was given initially, which is 0.103 molar, and then multiply by 100 because we're talking of a percentage. And so this is going to give us 92.0%. Alright, that is it for that problem. Laws passed in many countries define a drunk driver as the one who drives with the blood alcohol, okay, that is the ethanol given level of 0.1% by mass or higher. The level of alcohol in the blood is determined by the redox titration involving the following half reactions, as we can see there. Titration of 50 grams of the driver's blood plasma required 38.94 milliliters of 0.0723 molar of potassium dichromate solution to reach the end point. Now, first one. Okay. Of the two reactions, identify the oxidation and reduction half reaction. So it ends up to here. Of the two reactions, which one is oxidation? Which one is reduction? Now, oxidation is loss of electrons, and then reduction is gain. Whenever we see electrons on the part of the reactants, that means they've been gained, and that's reduction. So the first half reaction is reduction. And then when we see electrons on the products, that means they've been lost, and losing electrons is oxidation. So the second half reaction is oxidation. Now the other question asks, deduce the balanced redox reaction. Okay, now look at these two reactions. This one we have got 6 electrons there, and then for the other one we have got, actually even that was supposed to be 12 electrons which were given. Okay, let's write it just the way it is, like that. So this is the reactions which we have. Now we want to deduce the balanced redox reaction. And so the first thing that we want to do is to balance the electrons. We have got 12 electrons here, we've got 6 electrons. So the one which has got 6 electrons, multiply it by 2. And so multiply just the whole of it by 2. And so we're going to have 2 Cr2O7 2 minus, and then plus 28 hydrogen ions, plus 12 electrons, and then to produce 4 Cr3 plus, and then plus 14 water molecules. The other one will just write the way it is. This is supposed to be a 2 there, so that is 2 as we can see from the formula given above. So C2H5OH ethane reacting with 3 water molecules to produce 2 carbon dioxide plus 12 hydrogen ions, and then plus 12 electrons. So we're going to divide this reaction at this point into two halves. What we can see on both reactions, we're going to cancel out. So you can see 12 electrons here, 12 electrons there. We can see 3 water molecules here, 3 water molecules here, 11 are going to remain, 11 water molecules. We can see 12 hydrogen ions here, and then 12 electrons there. How many electrons are going to hydrogen ions are going to remain? So 16 hydrogen ions are going to remain. And so now we're going to write that. So we have got 2 Cr2O7, 2 minus, and then 16 hydrogen ions have remained, and then we've got C2H5OH, and then the other side we've been given 4Cr3 plus, and then plus 11 water molecules, and then plus 2 carbon dioxide. So I've gotten only these things we can see here. Alright, so that is it. That is the net balance equation for the reaction above. And then another question: determine the percentage alcohol level in the driver's blood plasma. Determine the percentage alcohol level in the driver's blood plasma. So the first thing that we want to calculate is the number of moles. Okay, we've been told when you reacted 50 grams of the driver's blood, it required this much of potassium dichromate. So let's calculate the number of moles of potassium dichromate. Potassium dichromate we can find from there. This is where this ion came from, potassium dichromate, the chromate. Okay, so number of moles of this Cr2O7 2 minus is going to be equal to concentration times volume. The concentration been given from there as 0.0723 molar, which is mole per liter. The volume is 38.94 milliliters, which you can multiply by 10 to the power negative 3 to convert to liters, and that is going to give us 2.815362 times 10 to the power negative 3 moles. Okay, after finding the moles, remember, we want to determine the percentage of alcohol level in the driver. So the driver, what we need to use to determine about the driver is what? Is the alcohol which was gotten from the driver, from the blood plasma. Okay. Now we can see that number of moles of the Cr2O7 2 minus, what is the coefficient? That is 2. It should be equal to the number of moles of C2H5OH over what? The number in front is 1. So we've already determined the number of moles of the other substance, and so we're just going to go on and replace. That is 2.815362 divided by 2, and that should be equal to the number of moles of C2H5OH. So the number of moles of C2H5OH is going to give us what? Okay, this is times 10 to the power negative 3 from there. So divide that by 2. That is going to give us 1.407681 times 10 to the power negative 3 moles. So these are the moles of alcohol present in the blood plasma. And so let's convert these moles of alcohol to mass. And how are we able to do that? Of course, we know how to convert. We know the formula when we've been given the number of moles, and we know the formula for alcohol: C2H5OH. Determine its molar mass. We've got hydrogen as 1.008. We have got oxygen here as 15.9994. We have got 5 hydrogens multiplied by 1.008, and then we've got 2 carbons, each with 12.01 0.07. So if we sum the molar mass here, we're supposed to find 46.0688 grams per mole. And so mass is given by number of moles times molar mass. So the number of moles that you've determined is 1.407681 times 10 to the power negative 3. These are moles. And then multiply by the molar mass, which is 46.0688. This is in grams per mole. Of course, the more down and the more there is going to cancel out. And so that is going to give us 0.064850 174 grams. So this is the mass of alcohol in the blood plasma. Now we want to determine the percent alcohol. So this is how much alcohol is there in the blood. But remember, we took a plasma of that. That's the total blood that we took. And so determine the percent alcohol. That will be equal to the alcohol which is present in the blood, the mass of the alcohol present in the blood as 0.064850 grams, divided by the total sample of blood which was collected, blood plasma, which was 50.00 grams, and then multiply that by 100%. And so that is going to give us 0.129700348, which we can simply leave to four significant figures as 0.1297% alcohol in blood. Now the last question: did the driver exceed the legal limit? And how do you determine if he exceeded or not? We've been taught there. Laws passed in many countries define a drunk driver as the one who drives with blood alcohol level of 0.1 or above. Now this is 0.12. It is already above the value that we, the one which has been put on by legal institutions. And so yes, the driver exceeded the legal limit. Legal limit was exceeded. So that is it. Now the last question in this video, been given a 0.400 gram sample containing manganese dioxide with that molar mass, was reduced by reacting it with 100 milliliters of 0.1 molar ferrous sulfate solution in an acidic media according to the ionic equation shown. The excess ferrous sulfate solution was back titrated with 32.00 milliliters of 0.023 molar potassium dichromate in an acidic media as in the reaction shown. Now I want to calculate the percent of manganese dioxide in the sample. What have we been given here? Okay, we've been told the sample is that mass reacted with what? 100 milliliters of 0.1 molar ferrous sulfate. From the ferrous sulfate, that is where we are getting the iron 2 plus ions. Okay, ferrous sulfate is this. This is where we're going to get the iron 2 plus ions, we can see there. Now when we did react, there was some ferrous sulfate which was in excess, so some of this remained. Those which are present there are the ones which have been given as the initial moles. Okay, and so the excess ferrous was back titrated with what? 32 milliliters of 0.023 molar potassium permanganate. That means everything that remained when this reacted, everything that remained here came and was used up completely in the second reaction. And so to find how much was used up in the second reaction, I'm going to say first the number of moles of that, the dichromate, is going to be equal to concentration times volume. The concentration is 0.02300 mole per liter, and then the volume we've been given as 32. Now it is in milliliters multiplied by 10 to the power negative 3 to convert to liters, and that is going to give us 0.000736 more of what? Cr2O7 2 minus. So those are the number of moles. Now to determine how much iron 2 plus reacted with this dichromate, we are going to compare the mole ratio. So number of moles of iron 2 plus divided by 6 should be equal to the number of moles of dichromate divided by 1. And that is going to give us number of moles of iron 2 plus simply being equal to 6 multiplied by this. So that would be 6 times the number of moles of dichromate, which I've already found as 0.0000736 moles. And so that is going to give us 0.004416 moles of iron 2 plus. Okay, so these are the moles which reacted in the second reaction. Let's determine how many moles of iron 2 plus were present initially. So number of moles of iron 2 plus present initially is going to be given by concentration times volume, and that is coming from there. We are already given the concentration as 0.1 mole per liter, and then multiply by the volume, which is 100 milliliters. Convert that to liters by multiplying by 10 to the power negative 3, and so that is going to give us 0.01 moles of iron 2 plus. So if these were the moles which are present at the start initially, and then these are the ones which reacted in the second reaction, then how many moles reacted in the first reaction? So we do a subtraction in this case. So the number of moles of iron 2 plus that reacted in the first reaction with manganese dioxide, okay, that is going to be equal to the number of moles of iron 2 plus initially minus the number of moles of what? Iron 2 plus which were present, which reacted in the second reaction. So which reacted in this case with what? The dichromate. So the number of moles of iron 2 plus initial was 0.01. Those which reacted with dichromate is 0.004416. And so that is going to give us 0.005584 moles of iron 2 plus. Alright, so these are the moles which reacted in the first reaction. Now, how much of this reacted with this? We're going to compare the mole ratios. So number of moles of manganese dioxide over 1 should be equal to the number of moles of what? Iron 2 plus over 2, comparing the mole ratios. And so that will give us number of moles of manganese, or to being equal to number of moles of iron 2 plus. We've already calculated those as 0.005584. So just divide by 2. That is going to give 0.002792 moles of manganese oxide. So these are the moles which reacted. Now let's convert these moles to mass. So that to be mass, we know is given by number of moles times the molar mass, and the number of moles we found as 0.002792 moles. And then the molar mass for manganese oxide already given there as 86.94 grams per mole. So this mole and that mole is going to cancel out. So the number of moles that we are going to determine in this case is going to be 0.24273648 grams of what? Manganese oxide. So these are the only ones which reacted, which we can also write even to four significant figures as 0.24. This is a 2 here. 0.2424. Okay. 0 point, let me write this properly. I can't even see what I've written there. Okay, that is 0.24273648 grams. Now we can write that to four significant figures as 0.2427 grams of manganese oxide. Now the question is, calculate the percentage manganese oxide in the sample. This is the only one which reacted. This is the only mass that reacted. But initially we are given this much, which we can see here. So the percent of manganese oxide is going to be how much reacted, that is a 0.2427 grams, then divided by how much was given, which is 0.400 grams, then multiply that by 100%. And so that is going to give us 60.68% of manganese oxide. So that was the percentage in the sample. And that marks the end of this video. That hope that was helpful. If you want to follow more about the videos and be reminded whenever a new video clicks on, please be sure to subscribe and press on the notification button. Stay blessed.